This is Mrs. O'Neill for AP Chemistry, Chapter 5, Section 7, Enthalpies of Formation. Objective: calculating enthalpy change of a chemical reaction is really the enthalpies of the products minus the enthalpies of the reactants. So you learned the reaction method, right? Taking that reaction mechanism or multiple reactions, manipulating them, and then finding the overall delta H of a reaction that you truly want. Now we're going to do the summation method, which is really the shortcut method. Pause, fill in the blanks, read as you write, and then play to hear my words. So what is standard enthalpy? Well, it's really the formation of 1 mole of a compound from its elements with all of those substances in their standard states. So first of all, what does standard states mean? Well, 25 degrees Celsius, which is really room temperature, 1 atmospheric pressure, which is kind of where we're living, and then 1 molarity when we're making solutions. So sometimes you're going to see a delta H with a degree symbol, and that degree symbol just really means that that reaction was carried out under standard conditions, that 25 degrees Celsius, 1 atmosphere, or if we're making a solution, it would be 1 molar. So when does delta H then equal delta H of formation with that little degree sign? When the elements are coming together in their standard states to make that compound. In other words, that compound is being formed from its elements. So standard enthalpy of reaction, this equation is on your reference sheet. It's basically telling you that the products, the delta H formation product values minus the delta H formation of the reactant values. And remember, this NP, I know it looks kind of goofy, but remember those are the moles. We always want to multiply by the moles of our coefficients. So elements in their standard state, however, always have a delta H formation of 0. Why? Because that's how they exist. That's how they exist in nature. So there's no forming of it. That's just automatically how they exist. So for example, if we look at bromine here, bromine exists naturally as a liquid, but so there has to be some kind of, energy, heat energy, either gained or lost, right, when we go from a liquid to a gas of bromine. Same thing with oxygen. With oxygen, its standard state is O2. Ozone, even though it exists kind of as nature, it really is not the most stable condition. So how did we get these values? Because they're the heat of formation combined from their elements. So give this some thought. If you just heard what I said, you probably get the answer. So like I said before, ozone is not the most stable form of oxygen, and that's why it still has a delta H value. So it is always the formation of 1 mole, and that's why we see these weird reactions, these weird fractions as coefficients in our balanced equation. So sometimes we'll see a half of an element or a compound, but one of the reasons is because these formation reactions always want to be in 1 mole. So for example, salt. If we take salt, we have NaCl, but a balanced chemical equation is going to mean we need 2 moles of Na plus 1 mole of chlorine to give us the 2 moles of NaCl. Well, that's just a normal reaction. We want a formation reaction. So we only want 1 mole of that NaCl. So we have to change it and we have to reduce. We want to make sure we get these 2 moles of the formation of salt to 1 mole, which means 2 divided by 2 gives us 1, and 2 divided by 1 gives us that half of chlorine. So that's an example of why we see sometimes half and these fractions in a formation reaction. And again, if we look at sugar as another example, if we look at sugar, sugar compound is C6H12O6. So that means it's coming from those elements at standard states to form, right, the formation of that 1 mole of sugar. So why is the formation a reaction for these elements 0? Because again, that's how they exist in nature. They exist as that solid, liquid, or gas. Okay, so it doesn't have a, if it doesn't have a formation reaction, it's automatically 0, if that makes any sense. There has to be a standard. There has to be a point where we can kind of relate everything at 2. So there's no formation of bromine liquid because that's how it exists in nature. So let's look at some of these problems. So here's example 1. So I want to know what the delta H of this overall reaction would be. Well, this is a nice balanced chemical equation that they give us. They also have to give us a chart or some kind of data that tells us the delta H of formation of the CO as a gas. So this is how much energy is needed, and it's negative in this case, so it's exothermic. This is how much energy is needed for CO to be formed from carbon and oxygen. Notice for oxygen gas itself is 0, because that's how it exists in nature. Now, just as a forewarning, if this was O2 as a liquid, there would have been some kind of value. So just as a side note, they don't always have to give you the delta H of formation of any element in its standard state, because you should know that it is 0. So just keep that in the back of your mind. So if they don't give you a delta H of something, that might mean that it's automatically 0. Now, this is CO2, carbon dioxide. This also has an exothermic delta H value, because the amount of energy that the CO2 is required to form from its carbon and oxygen in its standard state is negative 393. Okay, so what we're going to do is we're going to put down the values of those delta H's of each of those individual substances, and then we're going to do products minus reactants. We also want to remember we need to multiply by those delta H's now, by the mole ratio, the coefficients. I also want to remind you, you do not change the sign, okay? So for the CO, we're going to take 2 moles of the value they give us. The oxygen stays 0. And again, for the carbon dioxide, we're going to also multiply by 2. But we're going to keep the sign because the products minus the reactants, again, the products minus the reactants is going to take care of changing any of that sign. So then you just do the math. Negative 787 minus the negative 221 gives us the negative 566 kilojoules for that reaction to occur. That's our delta H. And again, it's going to be exothermic because of that negative. So why don't you give it a go? So what I strongly suggest is find the value of 3 NO2s, find the value of 1 H2O, find the value of 2 HNO3s, and find the value of 1 NO2s. Then I would strongly suggest adding these up. I would strongly suggest adding your products up. Then I would take your overall product number minus your overall reactant number. So pause and see if you can do the math correctly. So again, that was my suggestion. The first spot would be to get all of those values and multiply by those coefficients. Second thing I said was take all of those reactant values and come up with 1. Take all of those product values and add them up, come up with a number. Then it's easy. Then you're just dealing with 2 different numbers instead of all 4 or even more if you're kind of adding all of those coefficients along the way. And then products minus reactants, as long as it's the formation. These are the delta H formation values, so you can do products minus reactants and getting negative 138.8. Again, if you're not getting that value, that means you're not doing some kind of math right or something's goofy with that calculator of yours. Okay, see you in class.